Bueno, pues buenos días de nuevo. Hoy tenemos a Víctor Rivilla, que se encuentra ahora mismo en el Observatorio Astrofísico de Arcetri, pero que esperamos que pronto se pueda incorporar al CAP con un contrato de atracción de talento senior y que le fue concedido hace poco. Y entonces, en cuanto la situación pues mejore, pues se podrá incorporar. En principio, creo que Víctor, que me lo confirme, creo que se va a incorporar a principios de agosto.
Correcto.
Y es verdad, si la situación sigue así bien, esperemos que se pueda incorporar el 1 de agosto. Y bueno, pues para contaros un poco sobre Víctor, tesis allí en el Centro de Astrobiología, algunos de vosotros pues lo recordaréis. Hizo la tesis con Jesús Martín Pintado y luego justo después pues se fue al observatorio allí en Arcetri, primero para trabajar con financiación de un proyecto de Leonardo Testi. Y ahora en los últimos 3 años, eso fue durante 2 años, y estos últimos 3 años pues ha disfrutado pues de un contrato en Marie Sklodowska-Curie. Y bueno, el título, ya veis, de la charla, Cosmic Origins of Life, cool, que ese era el proyecto que presentó a la Comunidad de Madrid. Y bueno, Víctor, cuando quieras, pues... bueno, antes de que empieces, sí que me gustaría pedir... bueno, creo que estáis todos con el micrófono quitado, perfecto, para que no haya así ningún tipo de interrupción. Y bueno, si no hay ningún problema, estamos grabando hace 1 minuto o 2. Vamos a grabar la charla. Si hay algún problema, por favor que nos lo digan. Y si no, pues continuamos. Así que, Víctor, yo creo que no hay ningún problema. Víctor, cuando quieras, puedes empezar.
Ok, perfecto, gracias. Good morning to everyone. First, I would like to thank the organizers for inviting me to give this online seminar. It's quite weird being here alone in my room without see you, but I hope to see you all soon, hopefully. So the title of my talk, you can see in the slide, is Cosmic Origins of Life. The origin of The origin of life is quite a complex topic that has been addressed from different point of view, mainly from the chemical and biological point of view. I show you here a nice plot, a nice diagram of a prebiotic chemistry review by Rivilla some years ago. In the diagram, you can see that from starting organic but inert molecules that you can see here. I hope you can see the mouse, right?
Yes, we can see.
So from these inert molecules with a certain level of complexity, you can go up in complexity when you move towards the right part of the diagram and start to form building blocks of life, and at the end, the first living organism. So I'm an astronomer, so what I can contribute to this complex topic is to put the problem in a wider context, and this context is the astrophysical context. And this has sense because we know that Earth was the only place in the universe where life we know that exists. And our planet was formed in a protoplanetary disk, like this one that I show you here in this nice image of protoplanetary disk obtained with Harvard. And this protoplanetary disk was formed in the interstellar medium of the parental molecular cloud. So what we are trying to do is to understand what is the chemical complexity that you can have in the interstellar medium that could fit the formation of planets and of stars and planetary systems. The molecules in which we are interested are not even shown in this diagram because are more simpler than these ones. It would be the molecules in which we are working on would be in this blank space at the very first step of complexity. I show you here some examples of the molecules I will present during the seminar. So within astrochemistry, we would like to answer two main questions regarding the origin of life. The first one, can the precursors of basic components of life can be assembled in the interstellar medium? And the second is if these chemical precursors can be transferred from the initial stages of star formation in the interstellar medium to star-forming regions and planets, and eventually contribute to the prebiotic chemistry that gave rise to life on our planet. We know that stars and planets form in molecular clouds. We can identify molecular clouds, as you can see here in the left diagram, in the left figure, as dark spots in the sky if we observe them with infrared or optical images. But if we use larger wavelengths in the centimeter of or submillimeter ranges, we can penetrate into the cloud and detect what is the material that is inside the molecular cloud. I show you here two examples of two molecules, M2H+ and SiO, that are telling us that within this molecular cloud there are some regions that are particularly dense that will form stars. These molecular clouds have typical densities of 10 to the 3, 10 to the 4 centimeter cubic, and they are quite cold, with temperatures between 10 and 20 Kelvin. And they are full of interstellar dust particles, and also they are full of molecules, which are the chemical content in which we are mainly interested. In these molecular clouds, there are some regions where overdensities appear, and they can start the formation of stars and planets. I show you here an artistic impression of the different stages of star formation that I will show you as well in each step. Very nice images that we are getting now with the current telescopes that we have now in our hands. First, we start with some overdensities that are called prestellar cores that will collapse and form rotating structures that will form a protostellar disk. These are the prestellar cores that form in these dark regions, observed with infrared. And so you hear now an example of a nice binary system of two solar-like protostars. These are two progenitors of our sun. Then we have to allow the accretion onto the central protostar, the system ejects material in a bipolar molecular outflow to conserve the angular momentum, and we are now getting access to these stages, and we can observe them clearly. This is a very nice image in which you see the circumstellar disk here in red, and a very nice bipolar outflow that is ejecting material away from the central protostar, which allows the accretion of more material. Then the system evolves with time. The accretion continues, and then you can start to see the protostar also in the infrared, because the natural material disappear with time, and you end up with a protoplanetary disk like this one you can see here, in which, thanks to very high angular resolution observations, we are now starting to see structures and these interesting dark rings here that we think that they are related with the formation of new planets. And at the end, we end up with a young solar system like our own. So what we want to do is to understand how the chemical complexity develops during the whole process of the star formation. And to do that, the best way of doing it is detect the chemical reservoir in the different steps of star formation, from the initial interstellar medium to protostars, protoplanetary disk, and solar system objects. This is a list of the molecules that we have detected so far in the interstellar medium. I know that it's quite tiny and you cannot distinguish them, but the summary is that we have detected more than 200 molecules, of which more than 70 have more than 5 atoms. And thanks to the advent of more sensitive instruments, we have been able to detect more and more molecules with time. I show you here a plot that indicates the number of molecules detected, the cumulative number of molecules detected in the interstellar medium as a function of time. As you can see, that is continually increasing with the years. And this is already telling us that interstellar chemistry is able to synthesize molecules with a certain complexity. This is the chemical table of elements that everyone knows. Show you now the astrochemical version of it. I have indicated with red those elements that have been identified in molecules that we have already detected in space. As you can see, there are not many of them, only I think 17, but the most interesting thing to me is that among these 17 molecules, we have elements, sorry, we have the 5 elements that are more important, that are key for life: carbon, nitrogen, oxygen, sulfur, and phosphorus. So in astrochemistry, we have 3 main tools to understand what is the chemical complexity that we have in the interstellar medium. We have astronomical observations, laboratory experiments, and chemical models. I have mentioned that we have detected more than 200 molecules in space, but I didn't explain how we do it. The principle behind that is quite simple. The molecules, you can see here a molecule here in the interstellar medium, they can move, they can vibrate, and they can rotate in space. And by doing that, they emit photons that we can detect with our radio telescopes. Each molecule has a very unique spectrum, so they emit at very certain frequencies. I show you here the example of 2 spectrum of a simple molecule CO, which emits only at several frequencies. Here is frequency, and in comparison, we have the spectrum of a more complex species, methanol, which emits at in thousands of different lines. These 2 spectrum here are recorded in the laboratory, and this led to me to the laboratory experiment part, and this is where lab entered the game. In the laboratory, we need to derive and measure with precision the spectroscopy of these molecules, because we need the fingerprint of each molecule to compare with the spectra that we are getting with our observations. So the way we do it is compare the individual spectra from the laboratory of the different species, and we try to know if they can reproduce what we are getting, the spectra that we are getting. This is just an example of a spectral survey we have done in a massive star forming region with ALMA, and we compare the spectra we are observing with the spectra in the laboratory to understand if the molecules are detected first, and not only that, we also can, comparing the spectra, the laboratory spectra with our spectra, we can determine the abundances of the molecules. And this is very important. We can determine how abundant a molecule is compared with molecular hydrogen, which is the most abundant molecule in the interstellar medium. And these molecular abundances, we use them as an input of chemical models. This is the third part of the third tool that we'll use, that allow us to understand how the molecules are formed in the interstellar medium. There are 2 main ways of forming molecules in space. They can form directly in the gas of our sources, astronomical sources, or they can also form on the surface of dust grains. This is an image of a dust grain, interstellar dust grain, which has a typical size of 4.1 microns. And these 2 stages, dust surface of grains and gas phase, are related. So the molecules can desorb, which means that they can evaporate to the gas phase, but they can also deplete. They can freeze out onto the surface of the grains. And the interplay between these 2 stages should be well understood if we want to know how the molecules are formed. I show you here a very, very simplistic way of forming molecules. This is dust grain. And these are some molecules that obviously are not to scale, that are in the interstellar medium. These molecules can rotate, can vibrate in the interstellar medium, but at certain physical conditions of prestellar cores, that are cores that will form stars, they are quite dense and very cold, which means temperature of 10 Kelvin or even less. In these conditions, the molecules freeze out onto the surface of the grains, forming an easy grain mantle. If a source of energy arrives, and for instance we can have impact of cosmic rays, these molecules can move through the surface, they can diffuse. At some point, they can encounter each other, and a chemical reaction can occur, forming a more complex species, as you can see here. But the molecules are still on the grains. We need an additional source of energy, which can be, for instance, the heating of a nearby protostar that is forming. The heating, the thermal heating of the protostar can increase the temperature, and then the molecules can evaporate to the gas phase. And once in the gas phase, as I mentioned before, they can emit photons that we can detect with our telescopes. So after this very naive explanation about the basic of astrochemistry, I'm going to focus on the molecules in which I'm interested. As most of you know better than me, for sure, there are three main basic components of life. We have nucleotides that store the genetic information, proteins that are responsible of metabolic activity, and lipids which build up the cellular membranes. In this seminar, I will only focus on the first, nucleotides. Nucleotides are formed by three basic pieces: phosphates, sugars, and nucleobases. In the last years here in the Observatorio of Arcetri in Florence, I have done several works trying to understand how the precursors of these three different pieces of nucleotides can be formed in the interstellar medium. Let's start with phosphates, and in a more general context about the chemistry of phosphorus in the interstellar medium. We know that phosphorus is synthesized in massive stars during their lives, and then is injected to the interstellar medium through supernova explosions. However, phosphorus is barely detected in space. We have some detection of the ion P+ in diffuse clouds, some simple molecules in the evolved envelopes of stars on the end of their lives, and phosphine PS3 has been also detected in the atmospheres of Jupiter and Saturn, but there are not many detections. And the reason behind that is because phosphorus is cosmically lower abundant. The abundance of phosphorus in the universe, as you can see here, is 10 to the -7, while in living organisms, for instance in bacteria, the abundance is much higher by several orders of magnitude. We are talking about 10 to the -3. And also compared with other elements in the universe, like carbon, oxygen, nitrogen, phosphorus is several orders of magnitude less abundant. This makes difficult the detection of molecules with phosphorus, and then as a consequence, little is known yet about the chemistry of phosphorus. And now we are trying to improve our knowledge about this. The situation in star-forming regions was even worse. Before 2016, we started to study interstellar phosphorus chemistry in detail. Only one molecule, PN, was detected in 5 massive star-forming regions, and that's all. Not much. So that's why we decided to observe a large sample of star-forming regions. We observed up to 33 different massive star-forming regions, and we were able to detect PN in 22 of them. And this already multiplied in more than a factor of 4 the number of new sources of phosphorus in star-forming regions. And this already told us that it's true that phosphorus is low abundant, but it's more abundant than we previously thought in the gas of star-forming regions. And this is interesting, as I will tell you in next slides. This was a nice result. We detect PN in a lot of sources, but I was more interested in PO, and you may imagine why, because PO, the chemical bond between phosphorus and oxygen, is the very basic piece of phosphates that is a key element of many biomolecules, as you can see here in the case of DNA. So we decided to search for PO in this region here, in a massive star-forming region called W51, because it was the one in which we detected a brightest emission of PN. So it was a promising source to detect these other phosphorus-bearing species. And we were lucky, and we were able to detect PO for the first time in a star-forming region through the detection of this nice quadruplet, which is very indicative of the presence of PO. And the first detection was a nice result, but even more interestingly, we discovered that PO, even it's more difficult to detect, that PN is more abundant than PN, at least in this source, in a factor 2-3, which was in good agreement with the subsequent detection of PO in a protostellar shock, where PO was also more abundant. So far, I have shown you observations that were done with a single radio telescope, which means that we didn't have information about the spatial origin of the emission. And this limits our understanding about how the molecule is formed. That's why we decided to use interferometer, which is composed by a large number of antennas. In particular, we use ALMA, which is composed by more than 50 different antennas that directly provides you images of the emission. I show you here the emission of SO in a massive star-forming region called FAGL 5142. And in different colors, in blue and red, I show you the gas emitting in SO at different velocities. I'm sure that you cannot see anything clear here. I am going to help you. What is going on here, thanks to the kinematics and the Doppler effect of the gas, we know that what is occurring here is that we have a star, a massive star in the center that is powering a molecular outflow that I mentioned before, that is opening this cavity in the parental molecular core. So this is again SIO, and this is the cavity that is opening due to this bipolar molecular outflow. This is emission of SO again, and here on the right side, I'm going to show you what we obtain at the frequency of PN. This is the map of PN, and these are the first map ever obtained of a molecule with phosphorus in the interstellar medium. You can see that phosphorus is not coming from everywhere, it's coming from very particular regions of the field, and in particular, they arise from the cavities of the walls of these cavities opened by the protostellar outflow. So we extract the spectrum in these different spots in the cavity walls of the outflow. And we not only detect PN, we also detect several lines of PO, the same quadruplet that we discovered in the other source previously. And again, and this was confirmation that PO in this region, in these different spots, is more abundant than PN in factors that goes from 2 to 8. So it seems that the PO is the main carrier of phosphorus in star-forming regions. We wanted to go a step further and compare, okay, we know more now about the phosphorus content in star-forming regions, in the gas that will form stars and is forming stars, but we wanted to compare it with the final product of the star formation. And in particular, we were interested in knowing how the phosphorus content can transfer to, could be transferred to our solar system. And to do that, we decided to analyze the chemical composition of the comet 67P Churyumov-Gerasimenko, which is considered, whose chemical composition is considered as pristine material from the early solar system. So to do that, to study the chemical composition of the comet, we used data measured with the European Space Agency Rosetta mission that you may know. It was a space mission that went to the comet and orbited the comet during several months, and even landed on the comet. And it has provided us a very complete view of the chemical composition of the comet. In particular, we have used data from a mass spectroscopy of the instrument Rosina. We were mainly interested on phosphorus, of course. It was known in the first analysis of the mass spectroscopy of the comet that was published by the PI of the instrument, Catherine Alqueth, back in 2016, that the phosphorus was present in the comet. You can see here a clear peak at the mass expected of phosphorus. So phosphorus, we were certain that phosphorus is one of the elements present in the comets, but at that time we didn't know if this peak was produced by atomic phosphorus or it was phosphorus forming part of other molecules, like for instance, the ones we detected in the interstellar medium, PO, PN, or maybe in more complex species. That's why we decided to analyze more data that were recorded by the Rosetta mission, and we were able to identify a clear peak of PO in the mass spectroscopy of the comet. So it was clear that PO was detected, and we also detected for other species like PN, phosphine, and CP that were not detected. And we were able to derive upper limits for their abundances. And we found that PO is not only the only present, is the one with the higher abundance. So it's the main carrier of phosphorus in the comet, with a ratio of PO-PN, for instance, of 10, which is even higher than we have found in star-forming regions. And this is interesting because we have found a similar result in the initial stages of star formation and in the later products of star formation. And it seems that PO plays a dominant role in transferring phosphorus from one step to the others. So this is why we call this in this work the interstellar thread of phosphorus. We have seen that star-forming regions are good factories of phosphorus, and in particular of PO. In this region here, we have some massive stars forming in the center, but there is indeed a cluster of stars forming. We don't only have one star, we have several stars forming. And an environment like this is indeed similar to the environment in which we think that our solar system was born. There is growing evidence that our solar system was not formed in an isolated core, but in a region containing low mass stars like our sun, but also massive stars. And the chemical content of this cluster could be transferred to the gas that was the parental gas that formed our solar system. And this was supported by the chemical thread, the similar results we have found of PO being the dominant phosphorus carrier in the 67P comet. And this can have interesting implications for prebiotic chemistry, because we know that comets during the early life of our Earth could provide, through bombardments, a large fraction of prebiotic chemicals to the Earth that could help to give rise to life. And in this sense, the phosphorus that we have detected in the comet could play an important role making available phosphorus for the first simple form of life in our planet. Okay, we have also worked about sugars, which are responsible to build up the backbone of for instance, DNA and RNA. The only sugar that we have detected in the interstellar medium so far is a glycolaldehyde, which is this molecule here. We have tried to detect more complex sugars like a glyceraldehyde, but still without success, but we are trying hard. So we decided to understand, okay, we have detected this, which is the simplest one. We want to understand how is formed in the interstellar medium. Even if the most simple one, the formation, understanding the formation of these species is not straightforward. I show you here a diagram of some of the routes that have been proposed to form glycolaldehyde in the interstellar medium. As you can see, it's quite messy, the situation. So our approach to this was to, okay, if you have a look to the diagram, there is one species that is common in most of the chemical routes proposed, and is this HCO molecule. So we decided to study in detail this molecule in star-forming regions at a high angular resolution. That was something that it wasn't done before. So that's why we decided to, again, thanks to the ALMA interferometer, to study the emission of HCO, which is the common precursor of sugars, in this region here, which is a very nice protostellar system called IRAS-16-293. These are two protostars similar to our young sun. And thanks to the ALMA observations, we were able to detect, as you can see here, the contours indicate the emission of HCO, overplot in colors the continuing emission, essentially this emission I show here in orange. So we detect HCO towards both protostars, and not only, we also detect other species that are chemically related, like formaldehyde, methanol, and also the simplest sugar, glycolaldehyde, who was the main goal of the study, understand how this sugar is formed. So what we did is to derive the abundances of these different molecules and to compare them with a chemical model that we developed, which included all the chemical pathways that were proposed to form glycolaldehyde in the interstellar medium. This is a simplified version of the chemical network that we have used, in which we have HCO and the other molecules that we have detected, H2CO, methanol, and finally the sugar. And I have indicated here different models that we have considered, and comparing the results of the models with the abundances we got from the observations, we conclude that the model that fits better the observation is this chemical model, Model A, which is based on the formation of glycolaldehyde from HCO and CS2OH. Although it's true that other of the model considered, which is based on the combination of two HCO radicals, can also contribute to the formation of glycolaldehyde. And this result was also supported, was in good agreement with independent works, also, both chemical modeling and also laboratory works devoted to the formation of glycolaldehyde. And the third basic piece of nucleotides are nucleobases, and to explore the formation of nucleobases, or better, the formation of precursors of nucleobases in the interstellar medium, we went to one of our favorite sources, which is located in the center of the galaxy. The region is called the central molecular zone of the galaxy. You can see here a nice images a nice image of the region. And it's a very good laboratory to study astrochemistry, because the chemical complexity in this region is very rich and allow you to detect many species and study them in detail. In particular, we study a molecular cloud in this region here, Sagittarius B2, that I zoom in here. This is the region in which we are interested, G plus 0.693, which is located close to these other sources. This is emission, dust emission of clusters of massive stars. The star formation activity here is very intense. So you have very powerful molecular hot cores here. But here, as you can see in the image, there is nothing. There is no clear sign of star formation here. But if you map the region and you study the distribution of the molecular gas, for instance, the distribution of methanol, which is relatively complex, the one I saw here, you can see that the molecular emission peaks towards this source. And that's why we decided to study it with multiple observations covering a very wide spectral range. And during the years, we have detected many species there. Here I show you some examples of the molecules, but we have detected much more than this. And this makes this source the perfect place for the detection of new species. And one of the first we tried was cyanomethanamine, and we were interested in this species because it's a possible precursor of adenine, one of the DNA and RNA nucleobases. This molecule presents two isomers, which are two different versions of the molecule. We differ only on the orientation of the atoms. In this case, the difference is in the hydrogen atom on the top of the molecule, which is oriented in a different way in these two varieties of the molecule. We detected the isomer in the source. It was the second detection in the interstellar medium with this species. It was detected before in another source in the galactic center. But the most interesting thing in this work is that we were able to detect for the first time the other isomer. And not only detection was interesting, it was interesting mainly because we discovered that this isomer that we detect for the first time is clearly more abundant in a factor of 6, more abundant than the other. And this means that the molecule is more abundant in a factor of 6, which is quite high, compared to what we previously thought. So a precursor of adenine is, we have seen that the precursor of adenine is relatively abundant in the interstellar medium and can be efficiently formed in the star-forming regions and in the gas that we form stars, new stars and planets. And what's next? Obviously, we are interested on improve our understanding of chemical complexity. We want to detect more molecules which are important for prebiotic chemistry, and we want to understand how they are formed. But we are putting down now our search of new species in the context of one of the current generally accepted theories of the origin of life, which was proposed to answer an egg and chicken problem. This originates because it's not clear if nucleotides or proteins arise before, during the first steps of the origin of life. And this is relevant because you need nucleotides to synthesize proteins and proteins to replicate nucleotides. So this is an egg and chicken problem, and a possible solution was proposed some decades ago, and it's called the RNA world, and suggests that RNA was the key species, that the key chemical compound that could play both roles, the roles that nowadays are than by nucleotides and proteins. So in the context of the RNA world, there are several prebiotic experiments. I show you here an example of Kitodai 2 years ago, in which they try, but there are many others experiments in which they try to, starting from simple inorganic and organic molecules that you can see here in the left part of the diagram. These molecules here we are detecting in the interstellar medium can form organic precursors and then building blocks of life, and finally functional polymers and the first form of life. This diagram is quite complex, it's quite diabolic, so that's why we decided to do our own simplified version with a subsample of species. I show you here some species that once detected in the interstellar medium and indicated with a solid box, while the molecules not detected are indicated with a dashed box. And in color arrows indicate different formation routes that have been proposed in prebiotic experiments and also in the interstellar medium. So what we have done recently and we are trying to do now is to detect more molecules that are important for the RNA world hypothesis of the origin of life. This one is a cyanomethanamine that I mentioned before that we detected in the galactic center. So this one, that's why this one is considered detected. And we tried the detection of others in this diagram. We started obviously with the simplest ones, which are the ones we have more hope to detect. We start with this one, glyconitrile, and we went to the data we have of this IRS-16293 binary protostellar system that I mentioned before, and we were lucky and we were detected for the first time in the interstellar medium in a paper published by Sandy Zheng last year. So this one is already detected, fine. We also put our eyes in all the species, in particular in this one here, which is urea. And in this case, we went to our favorite source in the galactic center, and we were able to detect also urea in a paper recently published by Izaskun Jimenez Serra this year. This is not the first detection, it's the second detection, because some months ago it was also detected in a Stafford region, but it's telling us that also urea, which is an important compound which could be related with the formation of cytosine, another of the DNA and RNA nucleobases, is present in space. So what we are trying to do now is to detect more species of this diagram and understand how they can be formed, if they are formed in the interstellar medium, and how they are formed, not only building blocks of nucleotides, but also of other important species like amino acids of lipids. So we hope to show you in the following months and years more exciting results arising from this interstellar search of molecules related with the origin of life. And I'm very happy to come back home to do this kind of work, especially in the environment of the Center of Astrobiology in Madrid, which I think is the perfect place to do this kind of work, which requires interdisciplinarity skills. And indeed, we are now working with people there, not only astronomers, but also chemists and people working on biology, whose contribution is crucial for this kind of work. And these are my conclusions. I hope to convince you that interstellar chemistry is able to synthesize chemical precursors of building block of lives, like for instance nucleotides, but not only, and that these prebiotic molecules can be preserved and transferred during the star and planet formation process, providing the very first ingredients, the for the origin of life. Thank you.
Muchas gracias, Víctor. Pues gracias por la charla tan interesante. Yo creo que podemos pasar ahora a la ronda de preguntas. Si hay alguna pregunta, pues lo único que tenéis que hacer es conectar el micrófono y simplemente hacer la pregunta. Yo creo que Miriam tiene una. Adelante, Miriam.
Qué rápido, no sabía si ibas a ver la mano.
Sí, sí.
Hola, Víctor, gracias.
Hola.
Sorry, do I switch to English? Or...
No, español va bien, no hay problema.
Vale. Creo recordar que has comentado que la mayor parte del fósforo se encontraba en forma de PO y no de PN.
Sí.
Entonces tengo dos preguntas. Uno, ¿es esto una sorpresa, dado que hay bastante más oxígeno que nitrógeno en el universo? Y la segunda es si con estas nuevas abundancias de fósforo se reconcilia un poco lo que has comentado al principio, que a pesar de ser un elemento que es muy común en la bioquímica, pues se conoce muy poco en el universo.
Sí, sobre la primera pregunta, es verdad que el oxígeno es más abundante que el nitrógeno, más o menos en un orden de magnitud en el universo, y esto te podría hacer pensar que efectivamente no es sorprendente que PO sea más abundante que PN. Pero en realidad, aquí el factor limitante no es el oxígeno o el nitrógeno, porque a efectos del fósforo tienes todo el oxígeno, todo el nitrógeno que tú quieras. El factor limitante es el fósforo, que es el que es mucho menos abundante. Así que no se traduce directamente las abundancias relativas de oxígeno y nitrógeno en las abundancias de PO y de PN. Por ahora hemos visto que creemos, y lo he dicho, que el principal carrier de oxígeno en moléculas, de fósforo en moléculas parece el PO, pero bueno, esto solo tenemos dos moléculas y una es más abundante que la otra, lo que nos lleva a pensar eso. Pero estamos intentando detectar otras moléculas con fósforo que quizá estén escondiendo una buena cantidad de fósforo también. Una de ellas es, por ejemplo, la fosfina, que es pH3, que pensamos que se puede formar bastante eficientemente en los granos, porque basta tener en la superficie de los granos fósforo atómico y lo puedes hidrogenar. Hidrogenar en los granos es bastante fácil porque los átomos de hidrógeno son muy movibles, se pueden mover muy fácil, relativamente fácil en los granos. Entonces puedes hidrogenar, formar pH, pH2, entonces pH3. Entonces creemos que puede ser bastante abundante, incluso podría ser más abundante que el PO, pero todavía no lo hemos visto. El hecho de que lo hemos visto puede implicar que no esté, o sea, poco abundante, o puede indicar que no lo hemos buscado suficientemente bien o en las zonas en las que podría estar. Entonces, tenemos varios proyectos en los que estamos intentando detectar el pH3, la fosfina, en sitios donde, según los modelos químicos, debería haber una cantidad medible de pH3. Y la otra pregunta era acerca de la disponibilidad de fósforo.
Que si los modelos de nucleosíntesis explosiva, bueno, perdón, que si con las nuevas medidas de fósforo, aunque acabas de comentar que esperáis que no sean completas, se reconcilia eso con las abundancias que se pueden producir en supernovas.
Sí, es algo que no hemos hecho todavía y es algo que nos gustaría hacer, visto que tenemos detecciones de PN en un sample, en una muestra grande de regiones de formación estelar masiva en la galaxia. Nos gustaría, que están situadas a distintas distancias galactocéntricas, nos gustaría hacer un estudio en función de la localización de la galaxia, para ver si hay algún tipo de trend en las abundancias de fósforo en la forma de PN con respecto a lo que te esperarías de la producción debido a la nucleosíntesis. Es algo que queremos hacer en el futuro, sí. Pero todavía no tenemos ningún resultado.
Vale, gracias.
¿Hay alguna otra pregunta? A ver, Carlos, cuando quieras.
Hola, ¿me oís?
Sí.
Sí.
Sí. Vale, muy bien. Estupendo seminario, Víctor. Me ha gustado mucho lo que has contado. Y quería comentar, bueno, porque sabes que además me interesa mucho esta conexión, ¿no?, entre la astroquímica y el posible mundo RNA, ya lo hemos hablado en ocasiones. Y en este sentido quería hacerte una pregunta que a veces ya he comentado con Izaskun. ¿Consideras que hay un límite superior a la formación en cuanto al tamaño y la complejidad química? ¿Un límite superior en cuanto a la formación de moléculas orgánicas en gránulos? ¿O por el contrario ese límite no existe y es simplemente, entre comillas, una limitación experimental, observacional que tenéis para ver moléculas más grandes? Por ejemplo, de 4 carbonos, de 5 carbonos. Más allá de los pHs y de los fullerenos de 70 que sé que se han encontrado, ¿no? Pero moléculas que puedan ser precursores de la química prebiótica o incluso monómeros interesantes de cara a los
Sí, es una pregunta muy interesante, difícil de contestar. Lo que yo creo es que tiene que haber un límite superior a la complejidad que podemos generar con la química interestelar, porque las condiciones en el medio interestelar son muy distintas a las que tenemos en la Tierra en términos de presión, temperatura, densidades. Entonces, un límite seguramente existirá, pero creo que estamos todavía lejos, espero, porque si no me quedo sin trabajo, de llegar a la complejidad que se puede generar en el medio interestelar. Yo creo que el medio interestelar es capaz de generar moléculas bastante más complejas de las que estamos viendo. El problema es el otro que tú dices, es que lo que estamos ahora viendo, que son moléculas con 12, 10, 13 átomos, con 3 carbonos, 4 carbonos, estamos ya al límite del nivel de detección de los instrumentos que tenemos ahora. Entonces, para detectar nuevas especies, cuanto más compleja es una especie, en general, menos abundante es y menos señal emite. Entonces, necesitamos instrumentos más sensibles para poder verlos. Entonces, sí, vamos a necesitar mejores instrumentos en las próximas décadas. Y bueno, hay esperanza también en probar algún otro tipo de técnicas que estamos explorando para intentar ver estas moléculas que yo creo que sí que se forman, pero que todavía no vemos porque están dentro del ruido de nuestros datos.
Ya, de acuerdo, pues muchas gracias y suerte con esa búsqueda.
Gracias.
Muy bien. ¿Hay alguna otra pregunta? Si no hay otra pregunta, yo sí que te voy a preguntar, Víctor, si sabes cuál es la molécula, la parent molecule para el fósforo atómico que se ve a partir de los datos de Rosina de la misión Rosetta. Si crees que ese fósforo atómico está relacionado con el PO que se ve, o si crees que puede venir directamente de algún otro compuesto.
Sí, del análisis de los datos de la espectroscopía de masa, el resultado es que la mayor parte, creo que alrededor del 80% del fósforo atómico está en PO. Así que el PO...
O sea, que lo que se ve del fósforo se cree que es el PO se rompe en fósforo atómico y oxígeno, y lo que se ve de fósforo atómico procede de PO.
Correcto.
Vale, y entonces ese PO, lo que vosotros decís en vuestro artículo, es que se forma por procesos de formación estelar, ¿no? Pues en choques.
Sí, creemos porque hay evidencias de que este PO, igual que otras moléculas, como moléculas deuteradas que se han visto en el cometa, hay evidencias de que se formaron antes de la formación en el cometa, antes de la formación del Sol. O sea, tienen un origen preestelar. Entonces, lo que pensamos es que en el gas preestelar que formó el sistema solar ya tenías esas moléculas, por ejemplo PO, que se formaron en clústeres de estrellas que contenían también estrellas masivas, que son objetos que son bastante eficientes en la formación de moléculas con fósforo. No entra mucho en el detalle porque no quería ser demasiado específico, pero sí, creemos que el fósforo que acaba, el PO que acaba en la cometa, se pudo formar en una fase preestelar de la formación del sistema solar, que viene de la región del clúster parental en el que se formó el sistema solar.
Esto a lo mejor es algo que se podría comprobar con el James Webb, a lo mejor en hielos.
Sí,
a ver si se ve
claro.
algún...
Sí.
¿no? ¿Estáis
Sí,
trabajando en algo de ese estilo?
No, tengo la idea, la tengo, pero hay que ponerla en práctica, porque es una de las cosas que se podrían intentar es observar líneas de fosfina, por ejemplo. Si fosfina es abundante como creemos que podría ser, hay líneas de fosfina que se podrían observar con el James Webb, directamente en los granos.
Vale.
Pero es muy challenging. Yo no sé si, porque habría que dedicarle bastantes horas, porque en cualquier caso el fósforo es poco abundante y las abundancias de moléculas con fósforo no son muy brillantes. Así que la señal que te esperas es poca y será challenging hacerlo. Pero bueno, hay que intentarlo.
Claro. Muy bien, muchas gracias. Creo que Jacobo también tiene una pregunta.
Hola, Víctor. Charla muy interesante, muchas gracias. Mi pregunta es mucho más general que las anteriores y es la siguiente. Nos has estado hablando de cómo las moléculas relativamente complejas se pueden crear en granos de polvo en el medio interestelar y decías, pues le decías a Carlos que todavía crees que hay como mucho rango, ¿no?, para poder crear moléculas más complejas. Mi pregunta sería, más allá de este entorno y del obvio de los planetas, tanto que tengan agua como el nuestro y demás, ¿qué otros entornos interestelares son lugares prometedores para que ocurra este tipo de creación de moléculas? ¿Hay otra gente trabajando en otros entornos o realmente esto es lo que hay? ¿O se forman en granos o ya realmente hay que esperar a entornos mucho más controlados y con temperatura adecuada y demás?
Ok, sí. Como he mencionado, hay dos maneras principales de formar las moléculas. Una puede ser en granos, que ofrece ciertas ventajas para la formación de moléculas, especialmente si quieres crecer en complejidad, y otra es directamente en la fase gas, en el gas directamente.
Sí.
Y también se pueden formar. De hecho, hay gente que intenta apoyar la formación de moléculas en fase gas y está explorando las posibilidades de pura química en fase gas para formar moléculas complejas y de acuerdo con sus experimentos, con sus modelos, se podrían formar también. Así que es posible formarlo en estas dos fases.
Y en el gas, pero en el gas entiendo que se darían reacciones menos complejas, ¿o estoy equivocado? Que sobre un grano donde pueden moverse y demás, ¿no?
Sí, es una buena pregunta y es un debate muy intenso que tenemos en la comunidad astroquímica, porque hay quien cree que en fase gas no se puede llegar a este nivel de complejidad, hay quien cree que sí. Es un debate abierto. Yo creo que para la formación de moléculas muy complejas es posible que tengas una contribución de ambas fases, fase gas y fase sólida. En algunos casos de moléculas hemos detectado y luego hemos hecho modelos químicos para intentar entender cómo se forman. Hemos llegado a la conclusión de que las dos posibles rutas de formación son relevantes. Primero, una es dominante durante las primeras fases de evolución, antes de que se forme la protoestrella, y una vez que la protoestrella nace, calienta el entorno y cambia las propiedades físicas, la otra puede jugar un papel importante. Así que las dos pueden contribuir, aunque en general creo que la química que puedes tener en los granos te permite generar mayor complejidad. El problema es que estudiarla, los procesos de difusión de las moléculas en los granos son muy complejos de analizar desde un punto de vista teórico. Así que es como un black box que estamos intentando, sobre el que estamos intentando dar luz. La gente que trabaja en teoría está intentando mejorar los modelos, pero ahí hay un margen de mejora muy grande, porque no solo tenemos el hielo que es congelado, que está cubriendo los granos, también tenemos lo que llamamos bulk, que es la parte inmediatamente más interna del grano, y creemos que también puede jugar un papel relevante a la hora de formar moléculas, y quizá moléculas más complejas todavía, que se pueden formar en la parte más interna y que pueden llegar a la fase gas si, por ejemplo, tenemos choques de alta energía que son capaces de, por ejemplo, romper los granos. Entonces, pero todos estos procesos son difíciles de estudiar. Hay también experimentos de laboratorio que intentan de darnos importantes pistas acerca de lo.
Vale, pues muchas gracias, fenomenal.
Gracias a ti.
Bueno, pues muchas gracias. No sé si hay alguna otra pregunta. No veo aquí nadie más. Bueno, pues yo creo que con esto podemos finalizar el seminario de hoy. Así que, Víctor, muchas gracias por el seminario tan interesante.
Gracias a vosotros.
Y bueno, ya simplemente deciros que el próximo viernes vamos a tener otro seminario. El ponente será Alejandro Mascareño, del Instituto de Astrofísica de Canarias. Y bueno, enviaré la información de cómo conectaros pues a principio de semana de la que viene. Así que muchas gracias por asistir y nos escuchamos en una semana. Muchas gracias, Víctor.
Hasta luego, gracias. Hasta pronto.
Adiós. Hasta luego.
Gracias a ti.